In this video, we will learn about function transformations. This is AP Precalculus topic 1.12. If you appreciate this content, please don't forget to hit that like button. In these images, g of x represents a transformation of a parent function f of x. If you add or subtract something on the end of a function, that is going to be a vertical translation of k units. And for example, if we do a f of x minus 2, that would be a shift down 2 units. On the other hand, when you add or subtract a number on the inside of a function, that's going to be a horizontal translation. And it's going to be the opposite of the way it looks. So if you see an x plus 2, that's actually a shift to the left by 2. If you see a number multiplying the front of a function, that's going to be a vertical dilation by a factor of a units, or rather a factor of the absolute value of a units, because if that number is negative, the negative sign is really a reflection over the x-axis. On the inside of the function, when x is multiplied by b, this is a horizontal dilation by a factor of 1 over b, or rather the absolute value of 1 over b, because if b is negative, that's actually a reflection over the y-axis. For example, if g of x is equal to f at 3x, this 3 is a horizontal dilation by a factor of 1/3. So you might sometimes hear this described as a horizontal compression or horizontal shrink. Whether it is a stretch or a compression, we call it a dilation. So this will be a horizontal dilation by a factor of 1/3. On the other hand, if x was being multiplied by 1/3 on the inside, this would be a horizontal dilation by a factor of 3. So this would be like a horizontal stretch, but we'll just call it a dilation by a factor of 3. Notice that any transformations that affect the x values will occur inside the parentheses with the x variable. So those will be things like horizontal dilations, horizontal translations, or reflections over the y-axis. Be careful. Transformations that affect the x values do the opposite of what they look like. So this minus 5 is actually a shift to the right by 5. And this 1/3 is a horizontal dilation by a factor of 3, not 1/3. Any transformations that affect the y values will occur outside the parentheses. This includes vertical translations, vertical dilations, and reflections over the x-axis. Transformations that affect y values do exactly what they appear to do to the y values. So this plus 3 will shift all of the y values up by 3. This multiplying by 3 is a vertical dilation by a factor of 3. Everything will be 3 times as tall. Example 1. Let g be a function that is a transformation of the function f such that g of x equals 2 times f at x minus 3 plus 1. Describe the transformations of the function f that result with the function g. Transformations that occur inside the parentheses are horizontal transformations, and they do the opposite of what they appear to do. So f of x is translated horizontally 3 units to the right, the opposite of what it appears. Changes that appear outside of the parentheses are vertical transformations. They work just the way they appear. So this 2 in the front means that f of x is dilated vertically by a factor of 2. And this plus 1 on the end means that f of x is translated vertically 1 unit up. Example 2. Let n be a function that is a transformation of the function m such that n at x equals negative 4 times m at 2x. Describe the transformations of the function m that result with the function n. To be clear, this is not negative 4m. This is negative 4 times the function m at 2x. Changes inside the parentheses are horizontal transformations, and they work the opposite of the way they look. So this 2 means that m of x is dilated horizontally by a factor of 1/2. Think reciprocal here. Changes that happen outside the parentheses are vertical transformations, and I need you to view the negative sign and the 4 as two separate transformations. So the 4 means that m of x is dilated vertically by a factor of 4. The negative sign is a vertical reflection. In other words, m of x is reflected over the x-axis. Example 3. The graph of y equals f of x, consisting of two line segments and a semicircle, is shown on the interval from -3 to 5. Sketch a graph of g on the same axes above, where g of x equals f at x plus 3 minus 4. The plus 3 on the inside is a horizontal translation left 3. The minus 4 on the end is a vertical translation down 4. So let's move each of the key points left 3 and down 4. Here are the key points, and here's the sketch. Example 4. The graph of y equals h of x has a hole at x equals 4 and consists of three line segments as shown. Sketch a graph of k on the same axes where k of x equals negative h at 2x plus 1. When we have dilations involved, I like to perform the transformations using a chart. So let's start by listing off the key points that we see, starting with this point right here, which is -4, -3. That's a -3. There's -2, 1, 0, -2, the hole at 4, 2, the actual value at 4, -1, and the endpoint at 6, 4. Changes outside the parentheses are vertical transformations. These will affect the y values. So I will make a new y value list by doing -y plus 1. I've included the two changes happening outside the parentheses. I think I will go ahead and generate those new y values now. So this is the opposite of y plus 1. The opposite of -3 is +3, and then plus 1 is 4. We'll have -1, and then plus 1 is 0. +2, and then plus 1 is 3. -2, and then plus 1 is -1. +1, and then plus 1 is 2. -4, and then plus 1 is -3. Changes happening inside the parentheses are horizontal transformations and will affect the x values. But don't forget, these are the opposite of what they appear. So this 2 is really going to be a horizontal dilation by a factor of 1/2. So when I put my formula for new x values, it should be 1/2 x. So if I apply that transformation to these x values, I get -2, -1, 0, 2, 2, and 3. Now we just have to graph the new points, the green points. So this initial endpoint, which was at -4, -3, will now be at -2, 4. So that's going to be here. Okay, so this is the new endpoint. The point which was at -2, 1 is now at -1, 0. So that's going to be right here. The point that was at 0, -2 is now at 0, 3. So that'll be right here. The original hole was at 4, 2. The hole will now be at 2, -1. So that's going to be right here. The dot, which was at 4, -1, will now be at 2, 2. And the final endpoint, which was at 6, 4, will now be at 3, -3. Let's double check this graph compared to what we know about transformations. This new green graph does appear to be sort of upside down compared to the original graph. That makes sense because we were expecting a reflection over the x-axis. Also, the green graph looks a little bit squished. It looks compressed horizontally, and that makes sense because this 2 right here is a horizontal dilation by a factor of 1/2. So this is a horizontally compressed graph. It should be a little squished in here. And the whole thing was shifted up by 1. Because it's upside down, that's a little bit harder to see, but that happened as well. Example 5. The domain of f from example 3 is the closed interval from -3 to 5. And the range of f is the closed interval from 1 to 3. Find the domain and range of g, where g of x equals 2 times f at x plus 3 minus 4. Let me be clear. This is not 2f. This is 2 times f at x plus 3. The endpoints of the domain are x values, so I've listed them here on this small chart. The transformation that affects the x values are inside the parentheses, and they are the opposite of what they appear. So this plus 3 is really going to be x minus 3. So if I do that to the original domain values, I'm going to get -6 and 2. So this will be the new domain, the domain of g. In other words, g of x has domain -6 is less than or equal to x, which is less than or equal to 2. Similarly, the endpoints of the range are y values, which I've recorded right here. The transformations that affect the y values occur outside of the function, the 2 and the -4. These happen just like they look. So my new y values, which will give me my new range, can be found by using the expression 2 times y minus 4. So 2 times 1 is 2, minus 4 is -2. 2 times 3 is 6, minus 4 is +2. So the range of g of x is the closed interval from -2 to +2. Example 6. The table above gives values for a function p at selected values of x. Let h of x equal 3 times p at 2x minus 1. Find the following values. Be careful not to read this as 3p. This is 3 times p at 2x minus 1. H at -1 just means substitute -1 for x right here. So h at -1 will equal 3 times p at 2 times -1. And then minus 1. So simplifying a little bit, we have 3 times p at 2 times -1 is -2. So let's use the chart to find the value of p at -2. So here's -2, and here's p at -2. So we have 3 times 1 minus 1, because p at -2 was 1. And of course, 3 times 1 is 3, minus 1 is 2. So that's the answer to part A. Similarly, h at 2 means plug in 2 for x right here. So h at 2 will equal 3 times p at 2 times 2 minus 1. So that's 3 times p at 4 minus 1. So that's 3 times p at 4 is 3. So 3 times 3 minus 1. That's 9 minus 1, which is 8. And one more time, h at 0 means plug in 0 for x. So h at 0 will equal 3 times p at 2 times 0 minus 1. That's 3 times p at 0 minus 1. So that's 3 times. P at 0 is negative 1. So 3 times negative 1 minus 1. 3 times negative 1 is negative 3. Minus 1 is negative 4. So that's the answer to part C. Example 7. The function g is constructed by applying 3 transformations to the graph of f in this order: a horizontal dilation by a factor of 3, a vertical dilation by a factor of 4, and a vertical translation by negative 7 units. If g of x equals a times f at bx plus c, find the values of a, b, and c. First, we have a horizontal dilation by a factor of 3. Transformations that affect the x values appear on the inside of the parentheses, and they are the opposite of how they sound. So instead of a 3 right here, we will have a 1/3. So this will give a horizontal dilation by a factor of 3. A vertical dilation affects the y values, and that will appear outside of the parentheses. And a dilation is going to be a multiplying factor in the front. So a 4 right here will be a vertical dilation by a factor of 4. A vertical translation by negative 7 units will be something outside of the parentheses because this is affecting the y values. And we'll stick that right here on the end. So that means a is 4, b is 1/3, and c is negative 7. Example 8. The table above gives values for a function h at selected values of x. Let k of x equal a times h at bx plus c, where a, b, and c are positive constants. In the xy plane, the graph of k is constructed by applying 3 transformations to the graph of h in this order: a horizontal dilation by a factor of 1/2, a vertical dilation by a factor of 3, and a vertical translation by 1 unit. Find the value of k at negative 6. Let's start by building an expression for k of x. K of x includes a horizontal dilation by a factor of 1/2. So that's going to appear on the inside of the parentheses, as horizontal transformations always do, and it will be the opposite of how it sounds. So instead of writing a 1/2, we put a 2, the reciprocal. Next, we have a vertical dilation by a factor of 3. This will appear in the front of the function, and it will appear just as it looks, 3 times h at 2x. Finally, we have a vertical translation by 1 unit. That shows up on the end as a +1. Now that we have an expression for k of x, we can find k at negative 6 by plugging in negative 6 for x right here. So this will be 3 times h at 2 times x. So that's 2 times negative 6 plus 1. Simplifying a little bit, k at negative 6 will equal 3 times h at 2 times negative 6 is negative 12 and plus 1. So k at negative 6 will equal 3 times. What is h at negative 12? Here's negative 12. Here's h at negative 12. So that's 3 times 1 plus 1. So k at negative 6 is equal to 4. Example 9. The function p is given by p of x equals 3x minus 2. The graph of r is the image of the graph of p after a horizontal translation of 4 to the graph of p. If r of x equals ax plus b, find the values of a and b. So r of x is the result of a single transformation of the function p, a horizontal translation of 4. In other words, r of x is going to equal p at x minus 4. All right? a horizontal translation appears in here, and it will be the opposite of what it says. So a translation of positive 4 will show up as x minus 4 on the inside. But we have an expression for p of x. We need to turn this into an expression for p at x minus 4. We know, for example, that p at 7 would be 3 times 7 minus 2. But if I can stretch your imagination a little bit, p at star will equal 3 times star minus 2. Or p at smiley face will equal 3 times smiley face minus 2. So following the same pattern, p at x minus 4 will equal 3 times x minus 4 minus 2. Now we just need to simplify. Using the distributive property, we get 3x minus 12 minus 2. Combining like terms gives us 3x minus 14. In other words, a is equal to 3 and b is negative 14. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.